Thank you. I want to express my utmost gratitude for the Linda Hall Library. I enjoyed reading extensive government material and from the library's strong collection. Everyone was ready to help me finding material and even suggesting others. And I had a good, enjoyable time over lunch. And it's my honor to speak in front of you to share my work at the Linda Hall Library. I'd like to emphasize 3 points today. First, I show that the Environmental Protection Agency had competing ideas, approaches, and goals to protect the environment. Second, I argue that environmental problems provided a unique opportunity for engineers to reshape technology as parts of solution, not just problems. Third, I argue that the expansion of the control technology approach generated other social and environmental challenges. So here's the outline. First, I will introduce the key terms and actors of our story and share an overview of my bigger research project. Second, I will tell you how the EPA structured itself to tackle air pollution in the beginning of the 1970s. Third, I will turn to the EPA's role and strategies to demonstrate scrubbers as a reliable and effective solution to SO2 pollution. Fourth, I will follow how the success of scrubbers demonstration expanded beyond the EPA. I will conclude with some thoughts about the co-production of engineering and regulation and implications of my research on federal environmental policy. Okay, so let's learn some basics for today's lecture. So when sulfur-containing fuels are burned, oxides of sulfur are produced. Among them, sulfur dioxide, SO2, has been found to irritate eyes, aggravate asthma, and damage lung functions. People with chronic respiratory disease, the young, and the elderly are most susceptible to SO2 pollution. When exposed to moisture, SO2 oxidizes into sulfuric acid, which comes back to the land and water as an acid rain. Acid rain also reduces agricultural and forest production and visibility and deteriorates building exteriors. When SO2 converts to sulfate, SO4, aerosol, it may stay in the air longer. An increase in SO2 emissions was closely tied to the rapidly expanding electric power industry. Electricity generation doubled every 10 years since the Second World War, and it accounted for 60% of SO2 emissions in the 1970s. Scrubbers, or flue gas desulfurizers, were first developed in the United Kingdom in the 1930s and have been used in Japan and Sweden. It was not until the late 60s that some US electric utilities installed limestone scrubbers on coal-fired power plants. Scrubbers were designed to remove SO2 from gas streams by chemical reaction. It was a more expensive option than other competing technologies, but it achieved higher efficiencies up to 90%. Scrubbers dealt with the end-of-pipe treatment in the coal-fired power plant's full cycle from coal to sludge. After coal is mined and transported to power plants, it is pulverized and burned in a boiler. While the heat is used to generate electricity, several byproducts are created. Fly ash, which is non-combustible minerals like ash, dust, and soot, can be captured in an electrostatic precipitator and transported to a pond or landfill. Sulfur dioxide is controlled by scrubbers, while lime or limestone react with sulfur dioxide in water, it's called wet process, or in the air, it's called dry process. As a result, sludge or gypsum are produced and transported to a pond on a landfill. So now we know what produced SO2 and why SO2 was bad and how scrubbers were designed to reduce them. So let's begin our journey with an important moment in 1973. In October 1973, the EPA held a series of public hearings in Washington, D.C. The goal was to review the status of power plant compliance with sulfur oxide emissions limitations. Witnesses represented power plants, trade associations, state agencies, vendors of scrubbers, and public interest groups. Power plants were the largest source of sulfur oxide emissions, and they had only a year and a half to comply with emission standards. Scrubbers were regarded as the most viable option. However, most power plant operators claimed that the technology was unreliable, produced too much waste, and the cost was too high. They instead preferred other cheaper options such as low sulfur core, higher smokestacks, and intermittent control systems. The main expert witness on scrubber technology was Frank Princiota from EPA's Control Systems Laboratory. He was a chemical engineer in charge of a scrubber section of the Research Triangle Park, North Carolina. As the EPA's primary point of contact for both vendors and operators of scrubbers, he was well aware of the up-to-date materials and process problems in currently operating scrubbers. In addition, he had operated and tested 3 prototype scrubbers at the Shawnee site, as well as his own pilot scrubber at RTP Laboratory. Princiota showed that the reliability problems already had been resolved. Princiota and other witnesses acknowledged that potential water and land pollution issues of the scrubber sludge. They promised to support research and development on regenerable scrubbers, which produced reusable sulfur compounds. At the same time, Princiota emphasized that 2 private companies had developed technologies to decrease the environmental effects. On cost, the EPA claimed that the power industry's R&D efforts were limited in scope and amounted less than 1% of their revenues. Princiota and other EPA witnesses compared the inaction and indifference of big American power plants with successful Japanese scrubber design and use. Today, I want to use the case of scrubbers to give you a window to my bigger project. It addresses how engineers and scientists and managers define problems of the environment and establish management regimes by combining technology with regulation. It focuses on the first decade of the EPA, especially the Office of Research and Development, and its laboratories in Research Triangle Park, North Carolina. I explore how differing attitudes toward the role of scientific research and control technologies in environmental regulation shape the EPA and its relationship with other government agencies, industry, and academia. I show a shift in EPA's priorities from stringent health-based standards to flexible technology-based ones. I started my research in response to 2 ways in which the EPA was discussed. Historian Edmund Russell has argued that the agency's focus shifted from non-human species to human health during its first 15 years due to the changes in public opinions and the nascent risk assessment method. Science and technology studies scholar Sheila Jasanoff has argued that the EPA's controversial regulation cases showed the emergence of new regulatory science, which conforms to agency guidelines and is accountable to Congress, courts, media, as well as professional peers. I found their arguments persuasive and relevant to explain the relationship between science, engineering, and regulation. Scientists took the initiative by monitoring pollution and health. At the same time, EPA regulators depended on science to set standards, establish and enforce regulations, and legitimize their place in the new field of environmental protection. Engineers supported science and regulation by developing and testing new technologies and maintaining databases. However, in my research, I found a shift toward the end of 1970s. Findings from archives, published documents, and interviews with mid-level engineers, scientists, and managers enabled me to argue that regulatory engineering is a better concept to analyze the EPA activities, as they became closely associated with the energy and economy issues. I define regulatory engineering as an approach to socio-technical problems in which engineering practices are incorporated into regulatory and organizational change, which in turn influences technical knowledge and identity formation. Engineers took the initiative in developing, demonstrating, and evaluating control technologies in consideration of their applications in regulation. EPA regulators set up pollution standards and attainment deadlines according to new technology-based standards like best available control technology. Health and ecological research became supplementary to technological development or regulatory demand. Scientists carefully followed to make sure these control technologies and regulations did not generate serious environmental and health effects. By focusing on the co-production of engineering and regulation, my research gives insight into how technical professionals establish their credibility and boundaries, and why solutions to environmental problems themselves often generate new technical and social challenges. It highlights organizational and epistemic backgrounds for current environmental policy and uncovers its invisible hand in remedying market and government failures. I found the following two approaches of the EPA helpful to understand the changes in the air pollution policy. A community health approach assumed that setting up the health-based standards would be the first and strongest step to alleviate rampant pollution. The proponents of this approach focused on identifying pollutants and exploring the correlation between major pollutants and human health indicators. On the other hand, a control technology approach assumed that implementing pollution control technology would be the first and most practicable step. Control technology proponents argued for the evaluation of available control options in order to bring quick reduction into reality. Most RTP, Research Triangle Park units, took the community health approach, but Princiota's lab was taking on the control technology approach. So here's an example of the community health approach. I have looked at the case of community health and environmental surveillance system, which was a research project on the links between air pollution and respiratory disease. By exploring how allegations about researchers' integrity ballooned into an agency investigation and an reorganization of the EPA, I revealed how the community health approach expanded and met resistance. CHESS was an ambitious project to integrate human and environmental health, but its sudden demise shrank the community health approach and opened up space for the control technology approach. Today's topic, the development of scrubbers to reduce stationary emissions from coal-burning power plants, is an example of the control technology approach. After the 1973 oil crisis, EPA engineers developed their interest in demonstrating the reliability and cost-effectiveness of scrubbers to curtail smokestack emissions. When they faced potential water and land contamination from scrubber sludge, EPA engineers acknowledged the issues and took the initiative in applying cross-media approaches at an interagency program. By broadening the control technology approach to include the community health approach in the federal program, EPA engineers expanded the scope and scale of the control technology and established firm credibility in Washington politics and in the scientific community. At the same time, they sacrificed EPA's initial vision of environmental and public health. Now we will turn to the status of air pollution prior to 1970, and I will also show the origins and the structure of the Environmental Protection Agency. And I will also introduce Frank Princiota and the Control Systems Laboratory. Prior to 1970, the federal government's role in air pollution control was limited. Based on a few legislations on air quality, the federal government provided funding for research and set up loose standards in consideration of available technology and cost. In the case of stationary sources such as power plants and industrial boilers, particulate matters drew the most attention. Being the major stationary source of air pollution, power plants had already introduced electrostatic precipitators to reduce particulate matters. So they were reluctant to introduce another pollution control technology. Meanwhile, air pollution from stationary sources became evident in every part of the country. State and local governments had limitations in controlling these pollution sources, and federal scientists and engineers set up stations, collect and analyze data, and maintain the monitoring network. The Clean Air Act amendments of 1970 authorized the federal government to set up national ambient air quality standards for pollutants such as particulate matter, sulfur dioxide, and other pollutants based on public health and welfare grounds. The standards were for ambient air quality, so not the air quality at the source. Maintaining the level of air quality was the primary focus, with no particular technology suggested to accomplish this. Nor were cost factors included in setting up the standards, in contrast to the previous laws. The standards were a strong statement from the community health approach. The 1970 Act also required the EPA to intervene the states if their plan to improve air quality failed federal standards. In 1971, the EPA published national standards, and the states were to submit an implementation plan within 9 months of promulgation. If plans were not submitted or seemed inadequate to the EPA could implement its own plans, considering public health, not economic or technical feasibility. The EPA's standards for the new air pollution sources were more challenging and definitive than its standards for existing sources. The 1970 Act required the EPA to set up a standard by considering the best system of emission reduction and reasonable application of demonstrated technology. This standard was called New Source Performance Standards, and it applied to new sources like new power plants. This was a reflection of the control technology approach. So you can see how those two approaches are mixed in the Clean Air Act of 1970. So Clean Air Act was the Congress's response to the polluted air, and the establishment of the EPA was one of the most sustaining efforts from President Nixon. At its founding, EPA engineers and scientists and managers faced several organizational challenges. First of all, EPA inherited several units from other executive departments, which it had to integrate into a coherent structure. So, air pollution control came from the Department of Health, Education, and Welfare, and it was the second biggest in scale. And water pollution came both from the Department of Interior and Department of the Health, Education, and Welfare. So it was a little difficult to incorporate those two functions into one office. And pesticides control came from 3 different departments: agriculture, interior, and human health, education, and welfare. So you can imagine how it would be difficult to manage the office for the pesticides control. And there were other units for radiation, solid waste, and noise and vibration. EPA organized its own offices in a way that research and regulation functions were separated from each other. So in the third column, you see air pollution control and water pollution control is in a big one office. And on your next column, you can see pesticides, radiation, and solid waste is in another big office. And the last column you see is the Office of Research and Monitoring, which is the predecessor of the Office of Research and Development. So having separate in-house research and regulation functions was an effort to find a balance between encouraging researchers to support regulatory needs and protecting them from overcommitting to the short-term priorities. The ORM, the research office, established 4 national environmental research centers, and each was assigned a functional focus. So the Research Triangle Park Center had a focus on health effects and air pollution. And most of the labs and offices of the Research Triangle Park existed before 1970 when the EPA was established. But the Frank Princiota's lab, the Control Systems Lab, moved from the Cincinnati Center to the RTP. And Cincinnati had a traditional focus on water pollution and solid waste control. You can see how different culture can be a little problem later on. There were some other challenges for the EPA. First, conceiving and establishing the federal environment was an important task. EPA managers focused on regional pollution cases across state lines. Cross-media pollution cases were also important. Defining the problem of the environment also helped forming an identity for the agency's workforce. At the same time, the EPA had to position itself among Congress, White House, and the other federal departments. Even though the EPA took the major responsibility for federal environmental management in the executive branch, other departments still competed for funding with the EPA on issues such as environmental monitoring, fuel economy certification, and energy-related pollution. The White House also intervened with policy decisions, and legislators and judges often voiced their opinions at congressional hearings or by judicial reviews. To understand how the control technology approach became prevalent in stationary air pollution control, we need to understand the key figure, Frank Princiota. Princiota's move to the EPA was an outcome of previous connections and coincidence. He received his chemical engineering degree at New York, and he did graduate work in nuclear engineering at Oak Ridge. After working at the Atomic Energy Commission and Hitman Associates, he moved to RTP in 1971. I interviewed Princiota about 2 years ago, and here I quote him. He asked me if I had interest to come overnight. I had known very little about environmental protection, quite candidly, so he took a chance on me, the environment not being much of my area. Environmental engineering as a discipline was still forming up in 1970s. So his connection to the AEC was not very unusual. There were quite a few nuclear engineers working beyond their initial expertise. As the offices and laboratories were reorganized, the EPA needed workforce with diverse educational and workplace background, so they looked to their existing supply of talent. Princiota's unit had new hires like him and people who moved from the Cincinnati's lab. Their diverse experience in government and industry benefited the execution of their mission in the Control Systems Laboratory. Let's take a moment to look at their mission. I highlighted the energy development and efficiency related phrases in red, and I also highlighted the environmental protection related phrases in blue. So you can see how those two goals are mixed in this short mission statement. I will revisit this mix and tension in the broader context later in my talk. Now I will detail how Princiota demonstrated scrubbers as a successful case of pollution control technology against its regulatory and technical alternatives. I look at a cooperative test project which EPA operated 3 scrubbers with the Tennessee Valley Authority and Bechtel corporations in Shawnee, Kentucky. In October 1973, the Arab-Israel conflict broke out. President Nixon announced support for Israel, and the Soviet Union supported the Arab countries. In protest, Arab members of the OPEC first reduced oil production and later declared an embargo against the US. Oil price went from $3 a barrel to $12. Power plants switched back to coal, and the EPA was concerned about the repercussions. The Federal Energy Administration, FEA, confronted the EPA by suggesting loosening the regulations. President Nixon asked the EPA Administrator, Russell Train, support the FEA, but he refused. Nixon was displeased, but unable to fire Train because of the growing Watergate scandal. One EPA manager called these events as the energy threat to the EPA, and claimed that Train stayed as the administrator because Nixon could not stay as president. Right at this moment, in October and November of 1973, the EPA held a series of hearings on sulfur dioxide control. For electric utilities, the hearings provided a once-in-a-decade chance to loosen the standards and delay the deadlines. Testimony came from small utilities like Kansas City Power and Light, as well as large ones like Tennessee Valley Authority and American Electric Power. Utility witnesses generally agreed that the supply of low-sulfur coal was limited and insufficient to achieve compliance with sulfur dioxide regulations only through fuel switching. They expressed a strong desire to use locally available high-sulfur coal. Although scrubbers could bring them into regulatory compliance, not many companies testified that they had plans to install the scrubbers. So what other options exist other than scrubbers at the moment? Switching to low sulfur coal was costly because of limited supply and transportation cost. Coal cleaning had also been adopted as a standard procedure from the industry. However, the power industry preferred tall stacks and intermittent control systems. Tall stacks was a way to increase the height of their stacks so they could better disperse the pollutants. So the higher the stacks and the cleaner the air, the local air becomes. And the ICS, intermittent control systems, was when plants experienced unfavorable meteorological conditions, they had options to using cleaner fuels or shutting down some units temporarily and reducing outputs at other certain plants, where most sources using ICS curtailed operation only a few days each year. So in 1973, the EPA proposed ICS and TS regulation, and it allowed it the use of ICS and TS only when either permanent production curtailment or delay of an attainment date was expected. Most utilities argued that scrubbers had problems such as unreliable operation, high cost, and environmental effects. They were so concerned about the sludge that they even put on advertisement in Wall Street Journal. And you can see environmental issues were used by the electric utilities to attack the EPA. Frank Princiota and other EPA witnesses made good contribution against utilities and state regulators who were dubious about the scrubbers technology. Princiota's persuasive strength came from his direct involvement with scrubbers testing and demonstration. The EPA had a cooperative project with the Tennessee Valley Authority and Bechtel Corporation, and the TVA provided the site in Shawnee, Kentucky, and constructed and operated the units. Bechtel Corporation, which was an architecture and engineering firm, directed the test, and the EPA supervised it. On the left side, you see 3 scrubbers of them, and on your right side, you can see those 3 scrubbers with the background of 10 smokestacks. Princiota also had a smaller size pilot scrubber at his laboratory, and here you see him on his scrubber. With data from the running scrubbers, Princiota pointed out the recent improvements from reliable operations. There were concerns of two major phenomena in operating the scrubbers: scaling and plugging. Scaling, a phenomenon where hard chemical deposit inside the scrubber, was found in many operations. And the other phenomenon was plugging, which was soft solids builds up inside the scrubbers. So Japanese Mitsui and EPA's Shoni resolved the issue by changing liquid-gas ratio and controlling pH within limits. And also the EPA TVA Bacter operations also proved that improved alkali utilization not only decreased plugging, but it reduced both the quantity of limestone input and sludge output. So the method enhanced the overall efficiency of the scrubber system. So the bottom photo shows how the plugging issue was resolved. The cost of installing and operating scrubbers was another important issue. Capital and annual cost for retrofitting scrubbers on existing plants were higher than those for setting scrubbers on new plants. While acknowledging that scrubbers could not apply to all, Princiota argued that plants which were ready to retire or small plants might find dry scrubbers attractive. It was less efficient but cheaper option, so which became very popular in late 70s and early 80s. While scrubbers were manufactured and tested in a few coal-fired power plants, the utilities industry in general were more inclined to accept toll stacks and intermittent control systems. The EPA regulators, both the top officials and mid-level managers, were slow in formulating a clear policy on this issue. It was a series of ad hoc responses to individual requests for advice. In the gap between industry's preference and regulators' inaction, engineers at the EPA found scrubbers the most advanced technology to meet the standards by the 1975 deadline. The rest of my presentation will talk about the environmental effects of scrubbers. I will explore how Princiota achieved by redefining sludge-generated water and land pollution as another regulatory engineering problem. I will first look at the CSL's efforts to promote regenerable option and gypsum to claim the market competitiveness of scrubbers. Then I will show the change in EPA's strategy on the environmental effects of scrubber sludge, from not generating sludge to minimizing the environmental effects of sludge. Engineers at the CSL invested their energy into two types of scrubbering, a throwaway process and a regenerable process. The throwaway process removed sulfur dioxide from the flue gas and disposed of it. The regenerable process retrieved sulfur or sulfuric acid out of the flue gas. The regenerable scrubbers did not prosper in part for their higher price. And using extra energy for the regeneration was not attractive to the utilities. Even though the regenerable process did not win, the existence of this option helped Princiota to fight against concerns about the sludge. EPA's another card for sludge issue was converting sludge into synthetic gypsum, which can be used as construction material or crop nutrient. CSL engineers developed a new method to produce saleable products, gypsum, but concerns about possible leaching still existed. Princiota organized and chaired EPA's six-member evaluation panel on sludge, sulfur oxide throwaway sludge evaluation panel, SOXA. In its 1975 report, panelists first argued that all other alternatives are still emerging technologies and economically not competitive. They acknowledged that sludge-generated waste management had become an important hurdle for both utilities industry and the government. Federal regulation was not present, and the state and local agencies had been using existing solid waste, water, or hazardous waste regulations to treat sludge. For sludge and gypsum disposal, pond and landfill were the most popular options during the 1970s. The SOCSEB acknowledged that environmental effects of these disposals with ponding, soluble materials may cause the pollution of surface water and groundwater. Non-settling, physically unstable materials may cause land degradation. For the landfill option, the sludge must be dewatered or chemically treated before hauled to the site. The panelists asserted that extensive R&D program would resolve any issues. However, sludge and gypsum have reached human body through various pathways. Princiota and CSL engineers reached out of their comfort zone to address sludge-generated pollution and found their efforts rewarding. They expanded the realm of engineering approaches to water and land contamination issues. With successful inclusion of water and land pollution into their research and demonstration program, Princiota provided a blueprint for the cooperation between engineering, science, and regulatory functions in the agency. Once scrubbers became a de facto standard for sulfur dioxide reduction, reducing sludge's environmental effects became a critical passage where engineers, scientists, and managers wanted to pass before they proceeded to their next problems. This collaborative project expanded beyond the EPA into the larger energy issues. The White House established the Federal Interagency Energy Environment R&D program in order to coordinate energy development and environmental protection activities in more than 15 government agencies. The newly established Energy Research and Development Administration, which is the predecessor of the Department of Energy, didn't get the overall coordination and planning role. The EPA took this role, and the CSL became the core of this federal program. The rationale behind this choice was twofold. First, the EPA's primary mission was environmental protection, and the ERDA's mission was energy development. Second, the CSL's recent achievement, the scrubbers demonstration and SOCSEB activities, also gave an institutional advantage to the EPA. The structure and major activities of the federal program also reflected how the CSL's control technology approach had expanded beyond the EPA. Research, development, and demonstration activities were classified into two categories: control technology and health and environmental effects. The control technology category included not only conventional technologies like scrubbers, but also included fuel extraction, processing, and beneficiation. The health and environmental effects included ecological effects measurement and health monitoring. The increased role of the control technology is shown in ORD head Stephen Gage remark in 1977 conference. Here I quote him: "We need to control technology bridge to give us time to develop the miracle technologies, such as fluidized bed combustion in the midterm, and coal gasification, oil shale, solar, and nuclear fusion over a longer term." So you see a bridge metaphor is used for Stephen Gage. On the other hand, the ORD's health and environmental effects head, Delbert Barth, expressed concerns about the rapid expansion of the control technology. Here I quote him: "The good news is we are getting a national energy policy. But there could also be some bad news. Since the energy policy means expanded core use, some severe health and environmental impact could result from that expanded use." So the community health approach occupied supportive status in this interagency program. However, the two approaches, which originated from the EPA's RTP laboratories, functioned as productive tensions at the federal level. Princiota's successful demonstration of scrubbers in reducing stationary air pollution and subsequent expansion of the control technology approach to energy issues marked important changes in air pollution regulation. Engineering and regulation became co-produced. These changes came out of Princiota's peculiar position at the CSL. Princiota had great advantage in collecting and disseminating information on scrubber manufacturing and operation. In addition, he also generated new knowledge about the reliability and cost. As scrubbers became a standard for stationary air pollution, and subsequent technology-based regulations reflected this change, the Clean Air Act amendments of 1977 reflected the availability of scrubbers and its operation, and introduced concepts like bubble banking and offset of emissions to overcome the limitations of pre-existing approach. Scrubber's success provided an important leverage for engineers and managers to open up new markets where industry found more incentives to meet the emission standards. Princiota and his colleagues' approach to the environmental effects of scrubbers was another point worth mentioning. Instead of minimizing the scale of the problem, the EPA engineers acknowledged the problem and shared the most current information with the industry. At the same time, they used it as a way to draw more funding to initiate new projects. So the scrubber sludge was a successful case of resolving stationary air pollution by converting it into other types of pollution or engineering solutions. Health researchers who followed the community health approach in the Federal Energy Environment Program became marginalized by the expansion of the control technology approach. Princiota's demonstration of scrubbers became a powerful tool in elevating the control technology approach in energy and environmental policy. The Control Systems Laboratory provided substantial support to the planning of new energy environment R&D activities. Then what are the consequences of this expansion of the control technology approach beyond the EPA? Although the newly established Department of Energy took over the coordinating role of this federal program in 1979, Princiota and his North Carolina colleagues continued developing other technologies such as nitrogen oxide, radon, and CFC throughout 80s and 90s to tackle the thorny environmental issues of the time, acid rain, cancer, and ozone depletion. Continuing his control technology approach in mitigating climate change, Princiota recently published an edited volume titled Global Climate Change, The Technology Change. In addition to downscaling human needs and developing low-carbon, low-resource technologies, Princiota argued that technological measures to change Earth's heat transfer characteristics to compensate greenhouse gas emissions is worth analysis. Another publication, he emphasized his point. I quote him, "It's the author's opinion to consider geoengineering options, which although radical in concept, could potentially buy the time we may need to make the necessary adjustments in our energy and industrial infrastructure." So here's another bridge metaphor. Despite the former disclaimer that these ideas do not necessarily reflect the EPA's views or policies, quite a few environmentalists became concerned about the EPA senior managers' outspoken support of the geoengineering approach. I hope today's lecture on the rise of a control technology approach in federal air pollution policy contributes to our understanding of how one-time savior of the smokestack sulfur dioxide emissions became one of the supporters of the planetary scale engineering.
We have time for some questions. If you raise your hand, we're, of course, as you can see, we're videotaping the lecture, so we'd like to capture the audio of the questions. So raise your hand, I'll come by with the microphone. Don't be shy.
I think that you didn't address this, but it really seems that in the current age, building into what you've discussed, the whole concept of carbon credits is what's ultimately going to control these emissions. And I assume that that's what this last slide was alluding to, Art, that social issues here are going to become a huge part, where, in addition to the technological issues that are forcing the issue. Comment on the carbon credit issues.
Yeah, while doing research for this historical issue in the 1970s, I could find some analogy that I can relate the ongoing discussions about the carbon credit and the market approaches to the not only sulfur oxides but nitrogen oxides and CO2. So one of my findings from the historical research, which could be related to the current issue, is it's not just about the economist who designed the best offset or trading mechanism for the EPA or the utilities. It was also related with the technology, control technology that was available, and also it was related with the laws that supports those control technologies. So I agree with you that this big issue of environmental challenge could not be approached either by technology or nor by law or even by economics. We need a comprehensive approach to deal with these issues.
Excuse me, can you refresh my memory? When was the work done at Shawnee? When were those scrubbers operated by Princiota and the EPA and TVA?
Began in 1969, and it operated its scrubbers into the, I believe, 76 or 77.
Is there any, two questions. Is there any applicability to getting mercury out of the effluent from the power plants? And then a second question is, do you have any information on how extensive scrubber technology is being used in other parts of the world like China and India, where there's fairly extensive building of coal-fired power plants?
So on the issue of mercury, I have only basic knowledge about it, and from my understanding, the electrostatic precipitator and also scrubbers can be used to reduce the mercury emission as well, and it has been researched by EPA researchers and other independent or corporate researchers. So there is a possibility. And the second question about whether this technology is used in other parts of the world, I think it's becoming more of a standard to build scrubbers when they planning the electric utilities. But the old power plants, as I mentioned, putting scrubbers into the existing power plants are more expensive than building it when they planning the new power plant. So it's getting better in terms of putting scrubbers into the new power plants, but the old power plants that we have, it's not easy to put scrubbers on them, and in some cases, electric utilities industry argued that they need to have those power plants for the certain of local residents. So it has been an issue.
Thank you for your nice lecture. I have a question about this last slide. And you mentioned that Dr. Princiota talked about geoengineering. And then I wonder, if we look at the climate change right now, the technologies aren't as proven as scrubbers were back in the 1970s. There was some proof, you said, even from the UK and Japan using them. And I wonder how the metaphor works if what we're talking about now is geoengineering at an untested and unproven place?
I'm not an expert on geoengineering or planetary scale climate change technology, but what I can say as a historian or SDS scholar is we can learn from the lessons that we just saw from the 1970s case. So if there can be some discussion about whether, like, how much technology, what type of technology we can introduce to the testing rather than the full-scale demonstration or application, and it is also like Princiota's idea is not just like proposing this as the only option. He's also interested in other like issues like downsizing the human activities and also looking for renewable technologies. So the historical lesson shows that we need to talk about these options more than less. And it's not just engineers' responsibility to talk about this, it's also the public who needs to be engaged.
Back of the room here.
So are nitrogen oxides not that much of a problem in burning coal?
Question, and that part I couldn't talk about in my lecture, and it was less of a problem compared to sulfur oxides from the coal-fired power plant. And the control technology approach was used to the nitrogen oxide issues in late 70s and 80s, and it was quite a successful application of control technology approach to this stationary air pollution issue. So it's been more, it has been used in nitrogen oxides in later time period. And another thing that I want to add is, however, nitrogen oxide issue was still important for the 1970s history because the nitrogen oxides coming out of the automobile was a much more bigger issue at the point, and it was much harder to regulate compared to carbon monoxide or sulfur oxides, and we still trying to find more of a technology that can reduce nitrogen oxides from the automobiles, and catalytic converters are one of the technology that was used for the automobile emission to reduce nitrogen oxides.
Man?